Assalamu alaikum. We have a question here on normal and tangential components of acceleration. We have a motorcyclist at A increases his speed along the vertical path at the rate of 0.04 s feet per second squared, and s here is in feet. If he starts at A 2 feet per second, so that's the speed at A, and s is 0 at A. Now the question says determine the magnitude of his velocity when he reaches B and the initial acceleration. So now we need to find VB, right? And I need to find A at point A. So that's our initial acceleration. Now here the question says here, this point here, S is 0, right? And notice that he's going to follow through this arc, right? So that's the arc. Okay, now what do we have here? We know from this question, we have this acceleration given to be 0.04 s. And now v dot here is the acceleration. So this is the rate of change of velocity, right? And now we can say that v dot is just 0.04 s. And now since here we have the s, we need to choose the kinematic relation which has s, right? So now I can say v dot simply is dv over dt, so equal this 0.04 s. And now I can use the chain rule to introduce my new variable s, because here it is suitable to choose s since we have s here. So now I'll say I have dv over ds over dt, right? So 0.04 s. Okay, and now ds over dt is simply v, right? So again, I know that many just memorize the the relation, but I always use this so that I will never like forget this relation. So we have now v dv over ds equal 0.04 s. Okay, and now we can just separate the variables and integrate. So now I can say v dv equal 0.04 s ds. And now if we integrate both sides, I'll have here integration and here integration sign. Now about the integration limits, see the following here. What do we start with? I mean, what are the limits for the v integral? Now notice the following, we are going from A to B, right? At A, the velocity is 2. So now I'm going to put the lower limit for my v to be 2. And I'm going here to say just v. We can say this is really vb, right? I'm looking for a number, so this is just vb. And now for s here, what is my value for s? Now, since we start from 0 here, this is simply 0. I mean, the lower limit for s. Now, what about the upper limit for s? Look at this arc. Okay. Now, what we can say this s, I mean, the arc length here equal to the radius of curvature, rho, times the angle theta, but this theta now has to be in radian. Okay. So now if you apply this here, I will be able to calculate the length of this arc, right? So now substituting rho is given to be 300, and now rho in radian, this is 60. So if you convert that to radian, it will be simply pi over 3, right? So 180 over 3 is 60. So here times pi over 3, and now this is just 100 times pi. So that's my upper limit for the integral for s. So this is 100 pi. Okay. So now we just need to do this integral and substitute the limits. Okay. So now I have now v squared over 2 from 2 to vb equal 0.04 s square over 2 from 0 to 100 times pi. Okay, I can of course cancel this 2, so I'll have now vb square minus 2 square equal 0.04 100 times pi square minus 0, because here we have the lower limit for s is 0. Okay, so I can solve for that, and simply now I have evaluated VB. So now I found VB, found this to be 62.86 feet per second. Okay, and now what about the acceleration? Now the second question here, what is the initial acceleration at A? Now at A, notice the following, that we have, generally speaking, at A I have A tangential, right? So let me say AT at A and A normal at A, right? Equal. Now AT, now we have this, right? So this is like where we start, where the motorcyclists start to increase the speed. But now here we have S0, right? So we have, this is just 0. Plus, now AN is V square at point A over rho. And A is given to be 2. So we have 2 square over 300. And now that if you do this, you have found this answer is 0.0133, okay, feet per second square, and this is the initial acceleration. Okay, I hope you found this video useful. Please don't forget to like and share the video, and let us know in the comment if you have any question or suggestion. Okay, wishing you all a very good luck.